Okay. Okay. Today we're going to really start to get into the meat of the course. We're going to be talking about probability with discrete random variables, which we'll spend a few sessions on. After today, it's one of the things that you have to really be able to get yourself to understand before you can do, probability with continuous random variables and other things like that. Okay, as mentioned, although not everyone was here on Tuesday, even though we're not talking about Stan today, and we won't actually for a little while, Columbia has a number of grants to develop Stan, which is the software we'll use later in the course. I, along with a former QMSS student, actually do business-related stuff with Stan, and that creates the appearance of a conflict of interest that you should be aware of before listening to the rest of this presentation. Okay, so the first thing we need to talk about is a little bit of mathematical notation just to make sure we're all on the same page. This is probably stuff that you have seen before, and so I didn't explicitly put it on the syllabus, but if it's something that seems foreign to you, there's parts of the Moore and Siegel book which is on the syllabus. It's one of the textbooks we'll be using for the first part of the class. In its like first chapter or second chapter, something like that, it goes over things. So the first is the definition of what is a set. Set is just some collection of elements. In general, that can be either a finite set or an infinite set. So it could be intervals of numbers. It could be isolated numbers like 3, etc. And probably the most used set, at least for probability, is the set of all real numbers, negative numbers, 0, positive numbers. We won't be using anything relating to complex numbers in this class. So real numbers are basically the numbers that do have, or at least can have, decimal points associated with them, and as many decimal points as you want, even though for substantive purposes we're usually only interested in 1 or 2. Conceptually, there could be a lot more. So the integers 0, 1, 2, 3, etc., they're a subset of the real numbers, and those are denoted with the set empty z here. And those are just real numbers where all the decimal places are 0, particularly when we're talking about integers, but it could be any real numbers. We often exclude the negative numbers, which is indicated by a little plus subscript here. And today in this session, we're going to be focusing on a subset of the integers, really a subset of the non-negative integers, etc. And that all underscores the idea that these sets can be discrete. They can even be categorical. It's sort of like, what state do you live in? And it is sort of associated with a word rather than with a number. Second thing to sort of get our heads around is the definition of a random variable and a function. So a function is more general than a random variable. It's some rule that constitutes a unique mapping between each element of an input set and some element of an output set. So here we have a function that goes from the input set between any real number between 0 and 1. We have an output set that looks like it's all non-negative real numbers, etc. And you can see if you go anywhere on the horizontal axis here for the input set, it's going to correspond to exactly one member of the output set. So there's no looping or anything like that would make this merely a relation rather than a function. So the important thing about a function is the unique mapping from input set to a particular element of the output set. You might say, well, this particular function looks like a bijective function, which is to say we could start on the vertical axis here, go over to the curve, and end up at a unique element on the horizontal axis. That is true. That's going to hold for a lot of functions that we deal with this semester, but it's not required. What's required is to go from any element of the input set to a unique element of the output set, not necessarily the reverse. And a random variable is a particular type of function. And this is something that people seem to have a little bit of trouble getting their heads around, because you sort of think of a variable as it's represented like in a spreadsheet. It just sort of looks like a bunch of numbers. But we want to emphasize that a random variable, technically speaking, is a function from some set called the sample space, which we'll talk about more in a second, to some subset of the real numbers. And what makes this random variable a special type of function is it is going to have a probability-based rule defining the mapping from the input set to the output set. And we'll see examples of that in a second. So what is a sample space? Sample space is the set of all possible outcomes for some random variable that is observable. And this is typically, like a lot of things in statistics, denoted with a Greek letter. So one of the things you're going to have to deal with if you want to deal with probability, you have to deal with probability if you want to be a Bayesian, you have to learn the letters of the Greek alphabet. There's a bunch of them. They have lowercase letters. They have capital letters. But you need to know what they are. So what is this letter? Christina. All right. Very good. So if you did not know that, and you're not from Greece or Cyprus, need to get on that. There's a page of them in like the beginning of the Moore and Siegel book, or you can look them up on Wikipedia, but omega is certainly one. That is capital omega. Christina omitted that fact, but need to know that. So suppose you roll a die, just one of them. What are the possible outcomes of that process that is somewhat random, constituting the set uppercase omega? Yes, Martin. Or Merlin.
Yeah, integers from 1 to 6.
Integers from 1 to 6, correct. So one of the things that I think gives people trouble is conflating a realization of a random variable. So we roll a die, that's a process or a function. So rolling of the die is a function. Realization is some number like 4 that could come up, 1/6 of the time if you roll a die. So the 4 is not a random variable. 4 is a realization of a random variable. A random variable is a function, a process by which you take the die in your hand and you throw it. So don't conflate those two. And to make it easier to conflate those two, statisticians for many decades have been known to use a capital letter, in this case X, that's in the Latin alphabet, not the Greek, to indicate the random variable, the function, and the lowercase version of the same letter, little x, to be a realization of that random variable, such as 4. So when you're talking, you just sort of say X. But you need to keep in mind the distinction between the process and the outcome. Questions about that? All right. So one of my favorite examples for introducing probability is to think about bowling, which is a relatively simple yet somewhat random process, where each frame in bowling starts with 10 pins, and you get 2 rolls per frame to knock down as many of the pins as you can. So what would be the sample space for your first roll of a frame of bowling? There's the number 2.
0 to 10.
Specifically yes, so 0 to 10 are the endpoints.
Yeah.
And then what could be in the middle?
Yeah.
Right, any integer between 0 and 10. That constitutes omega, the set of possible outcomes on the first roll. All right. Also, we're going to use a lot over the course of the semester the vertical bar. This is read in English as given. So, probability of something given that something else is true. It does, even though we use this symbol in R, it means or. On slides, it means given. Okay. So there was a woman named Jennifer, I think, Hahn, who wrote her dissertation on bowling, which is not something that, traditionally in the QMSS, we really spend a whole lot of time analyzing bowling from a quantitative perspective. But then after Bob Putnam wrote that book about bowling alone, everybody started analyzing bowling, including this person, Han, who discussed a number of probability distributions that we could use to understand bowling. She named one of them after herself, which is only Gauss gets to do that. But anyway, this is actually, I think, one that her dissertation advisor came up with. Anyway, the University of Eastern Kentucky is apparently where you go to if you want to study bowling. It's probably the top bowling studies program in the United States, if not the entire world. Anyway, she discusses the probability of knocking down capital X pins, so that's going to be greater than or equal to 0, out of little n, where little n is conventionally 10, but she does a whole lot of other stuff for like alternative bowling games where you have more than 10 pins, and represents the probability of each realization, little x pins being knocked down out of 10, as this ratio f of x divided by -1 plus f of n plus 2, where these f functions are Fibonacci numbers. So f subscript x is the xth Fibonacci number. Fibonacci numbers are defined by a sequence where the 0th one is equal to 1. The first Fibonacci number is also equal to 1. And every remaining Fibonacci number is defined as the sum of the previous two Fibonacci numbers. So the second Fibonacci number would be equal to 1 plus 1, which is 2. The third Fibonacci number would be equal to 2 plus 1, 3, etc. So the first 13 Fibonacci numbers, there's an infinite number of them, are these right here. And interesting property of the Fibonacci numbers is that the sum of the first, however many, is equal to, 2 more Fibonacci numbers less 1. And so in the numerator here, we have the xth Fibonacci number. So if you knock down like 6 pins or whatever, little x would be 6. And it's divided by -1 plus the n plus 2 Fibonacci number, where n would be 10. So that would be the 12th Fibonacci number, starting with 0. Anyway, the sum of the first 11 Fibonacci numbers is 232, which is 1 less than the 13th Fibonacci number. Okay, so here's a little bit of our code that implements what's on the previous slide. This, you can look at the R Markdown file on Canvas. I also pulled this slide out is just a separate file. It's called code1b.r or something. It's on Canvas, or if you have R open, which you probably should, you can just source in this URL and it will give you a copy of this code, which you're going to need. So first I define a function called f, which is just going to return the Fibonacci number. Now, the way it's sort of traditionally defined with this recursive definition is, fine conceptually, it's sort of slow to evaluate in R. So there's another way where you just kind of do some stuff and round at the end in order to get a function that returns you the xth Fibonacci number. So R is a nice language because it allows you to define your own functions and then call them. But it doesn't come with a Fibonacci function, so we have to make our own. Next, I define another function, which I call PR. It takes two arguments, x and n, but n defaults to 10, and it's going to return the ratio on the previous page. So f of x divided by -1 plus the n plus 2 Fibonacci number. Now, I do this other stuff here, which is to implement something that's sort of implicit in the previous definition and the specification of the sample space. If n is 10, which it conventionally is for bowling, the probability of knocking down 17 pins out of 10 is what? 0. So that's kind of implicit in the definition, but you need to tell R that explicitly. So the if-else function takes a logical condition, and then if this is true, it's going to return 0. If this is false, then it's going to return the ratio of these two things here. So if x is greater than n, return 0. If x is less than or equal to n, return this ratio thing that defines the probability that we're using. So it can be shown, and it basically is shown here, that if you take all the probabilities of x, where x can be 0, 1, 2, 3, up to 10, and you take all these probabilities, which being the ratio of positive numbers are going to be positive, they all sum up to 1 across the elements, the 11 elements of the sample space omega between the integers 0 and 10. And you can show that that is a theorem relating to probabilities, that the sum of probabilities over the entire sample space has to be equal to 1. That's basically our convention about units, or our normalization of our probabilities. And so this function is going to satisfy that. I define my sample space, omega, 0, 10. If you're not familiar with the colon operator in R, it just makes a integer vector of consecutive integers, in this case between 0 and 10. And then I can take omega, stick it into my probability function, sum that up over all of these probabilities, and it comes out to exactly 1 by construction. And that means this is a valid probability distribution for bowling or anything else where you have like consecutive integers starting at 0 as the number of possible things that could happen. So how do we obtain a realization of this random process? In R, there's a function called sample, which you can use to get a realization anytime the sample space is finite. So we pass in our sample space omega, say we want a sample of size 1, and then we need to give it a vector that is the same length as omega, specifying what probabilities to use to take this realization. So we call our PR function, put the whole sample space into it, assign that to the value little x, and that's just sort of a R representation of the process of somebody rolling a bowling ball, and you see how many pins get knocked down. All right? So those of you who have R and have this file open why don't you look at what you get for little x? Again, you can just source in this line and it'll bring it in. What we got over here? Sophie?
I got 7.
Not bad. Not bad. Who else? 8. Better than Sophie. 9. We can do better than that. That's what I'm talking about. Good job. So why did we get 4 different things from the first 4 people who managed to source this in? The random process. We don't know exactly what's going to happen when somebody, grabs a bowling ball. Right? And so this is the sort of thing that we want to be able to use probability to analyze. All right. So think about what you got on your first roll. No cheating. Says you got 7, you got to stick with 7. And think about how we would calculate the probability that on your second roll of a frame of bowling, you knock down the remaining pins. How would we think about that? Not like the exact number, but how would we think about going about calculating something like that? Yes.
I mean, I would do this 1,000 times. It's how many times 7?
So the first roll, you would do 1,000 times.
So it depends on exactly on how they generate numbers. Sort of random and they see.
Yeah, well, for only taking one, there's a sort of technical issue with computers don't really do random numbers. They're more like pseudo-random, but you can consider them to be random. But we know the probabilities of knocking down, this or that number of pins on our first roll. It's just given explicitly by this expression here. How could we come up with an expression for the probability of knocking down the remaining pins on your second roll? Yes.
Replace the n by the number of remaining pins.
Right, and the number of remaining pins is?
For me, it was 0.
For you, it's 0. Okay, that's kind of a weird case. But for somebody else or in general, it's n minus x1. So in order to know the probability of you knocking down the remaining pins, you need to know how many are left. You might also want to know where they are. But that, like where they're located, that's a more complicated thing for how we would have to model something like that. So let's just simplify it to, if you have 2 pins remaining, the probability of knocking them down is the same, whether it's like the 610 and they're several feet apart, or that there's 2 pins who are right next to each other, and that's easier to knock down. Should have a higher probability, but we're not going to get into that level of complication for something like this. So that's right. And for those of you who got a strike on your first roll, knocked down all 10 pins, then there's 0 pins remaining. And so the probability, the second roll doesn't really happen in reality, but if you were to roll a second ball and there's no pins sitting there, then you're guaranteed to knock over 0 pins. So it's conditionally deterministic. And so you wouldn't even bother to roll the ball. But you can think of your second roll as achieving 0 pins because 10 were knocked down on the first roll. Questions about that? Okay. So we did that. In order to distinguish between the first and second rolls of a frame of bowling, we're going to define 2 random variables, x1 and x2, number of pins knocked down respectively on those 2 rolls. And so what in general would be a function that yields the probability of knocking down x2 pins on your second roll, where x2 could be all the remaining pins or it could be some subset. What would be a function that we can call to evaluate that probability? It's just a generalization, really, of what we just said. So what would it be in terms of this?
Probability of x2 given n minus x1.
Right. So we would put the x2 Fibonacci number in the numerator, and we put -1 plus the Fibonacci number corresponding to 10 minus x1 plus 2 in the denominator there. All right. So that is given by this, but there's an additional consideration that we have to take into account, and that's indicated by this so-called indicator function. So an indicator function is going to be equal to 1 if the condition inside it is true, and 0 if the condition inside it is false. So why do we need to multiply by this indicator function here? Yes. That is true, but even let's say you knock down 7 on the first, what would be the probability of knocking down 8 on the second? Right. So we need to multiply it by something that's 0 when there's impossibility happens, or impossibility doesn't happen, but just to make sure that we're confining our positive probabilities to things that can actually occur under the rules of bowling. Questions about that? Yeah. So the probability of knocking down x2 pins on your second roll, given that x1 pins have been knocked down on the first roll, and given that you started with 10 pins, is what's known as a conditional probability. And conditioning is what Joe Blitzstein, who wrote one of the probability books that's listed as optional on the syllabus, calls the soul of statistics. Really, like the essence of doing stuff with quantitative modeling at a high level of rigor is manipulating and utilizing these conditional probability expressions, functions, particularly for the case where you're given data information and you want the probability of something that hasn't happened yet. So we're like thinking between the 2 rolls of a bowling. And conditioning, this given thing, basically it's this fundamental idea, and it sort of means do this operation only in the subset where the condition holds. So the probability of knocking down like 4 pins, given that you knock down 5 pins on your first roll, is going to be different than the probability of knocking down 4 pins on your second roll, given that you knock down 3 pins on your first roll. Like all the probabilities change. And so you have to bear in mind that when you say, conditional on the first roll knocking down 7 pins or whatever it may be, that, what you do subsequently is all under the condition that the first thing happened, the first thing you know to be true, or you're at least taking it to be true. All right. So we talked a little bit on Tuesday that probability is sort of a weakening of Aristotelian logic, where things aren't just like absolutely true or absolutely false. We might encounter situations in which we don't know whether a proposition is going to be true or not, but we can use probability to express our degree of belief that a proposition is true. So in R, implements this idea of classical propositional logic. In a lot of other languages do this as well, mapping the keyword true to 1 and the keyword false to 0 when doing arithmetic operations on these things. And so we can use the ampersand to be the and operation. So if we have two propositions, both of which are true, then it's true that both of them are true. And so this can be alternatively represented in R by taking true, which maps to 1, and multiplying it by true, which maps to 1. And 1 times 1 is equal to 1. And so from R's perspective, both the left-hand side and the right-hand side are 1, and it is true that 1 is equal to 1. And so, if we have, two things like, is it going to snow tomorrow? And, is it going to be, the temperature less than, whatever? Is it the case that both of those are true? Well, if the first one is true and we multiply it by the truth value of the second one, we get true. Whereas if one of them is false, then you get 0 multiplied by 1, which is going to be 0. So if your condition requires two things to be true and only one of them is true, then the whole thing is false. Similarly, here, so if we have true, something that evaluates the true and something that evaluates the false, not both of them are true. And if we take true, multiply it by false, that's 1 times 0. So this evaluates the 0 equals 0, which is also a true statement from R's perspective. So how can we generalize this to probabilities, which are any real number on the 0, 1 interval, inclusive of the endpoints, to compute the probability that 2 or more propositions are simultaneously true? And to do that, we use the general multiplication rule, which involves this intersection symbol, and this can be read as and. So the probability that proposition A is true and proposition B is true can be represented by the probability that proposition B is true multiplied by the probability that proposition A is true, given that B is true. So those product of those two things is the probability that both are true. Alternatively, we can write this as the probability that A is true multiplied by the probability that B is true, given that A actually happened or does happen. Both of these two expressions over here are equal to the probability that proposition A is true and proposition B is true simultaneously. And this is what's known as the multiplication rule of probability. It's really taking the same rule that we use in Aristotelian logic for whether, 2 or more things are deductively true, and extending it to probabilities, which are going to be numbers between 0 and 1, but basically doing the same multiplication in order to come up with the probability that both are true. And this resulting number can be any number that's real between 0 and 1. All right? Questions about the multiplication rule or how it's, related to logic? Basically, if you take some proposition, like what's the probability that the sun is going to come up tomorrow? That's just, something that is like extremely close to 1. And so if you take two things like, what's the probability that it's going to be greater than negative 50 degrees and the probability that the sun is going to come up tomorrow, both of those are essentially probability 1 events. You might as well just take them to be probability 1 events, in which case you're going to be, it's sort of as a limiting case back to, Aristotelian logic. But if you take something that's more, germane, like what's the probability it's going to be above 35 degrees tomorrow? Well, then it's not, so close to being 1 or 0. It could actually be a probability that's like 0.5 or something like that. Questions? Ju?
Does that change that formula? Does that change of whether like the two probabilities with that's happening or
It does not change, but we're going to talk about that next. Does anybody have another question about the multiplication rule? All right. So independence, very important idea in probability. And loosely speaking, we say propositions A and B are independent of each other if A being true tells us nothing about the probability that B is true, and vice versa. But in general, things are not independent. So we need more of a formal definition. So we say A and B are independent of each other if and only if, that's what IFF means. The probability of A given B simplifies to some expression for the probability of A only that does not involve B. And the same thing the other way, probability of B given A simplifies to some valid probability expression that only depends on B, not on A. And these, two things together imply that in the case where A and B are independent of each other, the probability that A is true and the probability of B is true is simply the product of the probabilities that they're true respectively. So it's just some practice thinking about this. Why is it reasonable to think that two rolls in the same frame of bowling are not independent of each other? So like A would be your first roll and B would be your second roll? Robert.
Knock down the first time determines how many.
Right. So in your case where you knock down 10 on the first one, you were guaranteed to knock down 0 on the second. It was like the opposite of independent. It was deterministic given what happened on the first one. But even if you only knock down, 7, it's not the case that, you can just take the probability of, 7 and multiply it by the probability of 3 to come up with a probability of a spare. You need to be multiplying by the probability that you knock down 3 of the remaining 3. But why might it be reasonable to say two rolls, let's say the first roll in two different frames of bowling are independent of each other? Yes. Correct. So they tee up 10 pins for you, regardless of what happens, in the past or how much money you pay them or, anything like that. There's always going to be 10. But even for like the same person, why might not it be reasonable to think, the first roll of like consecutive frames of bowling is independent of each other? Becca.
If someone's bad at bowling, they need to be that.
Yeah, but if someone's bad at bowling, they might actually get better with practice.
But it's still, they might get better then, but then it's not independent related to
Right.
how they work.
So kind of the way we wrote it down, assume that there would be independence across frames. But, you might find yourself in the zone or something like that, in which case, the fact that you got a strike on your fourth frame tells you something more about the probability that you get a strike on your fifth frame. Or, conversely, if you get like a 0, things like that. But why might rolls of two different people be independent, even if they were both on like frame 3? Robert.
They're both, they're both looking at 10 pins. They have different skill levels. The fact that they're at the same point.
Yeah, certainly mechanically they're independent, but maybe if like two people in adjacent lanes start trying to roll the ball at the same time, one of them might distract the other or something like that. But that's more complication than we're thinking about today. But when you think about modeling something, you want to say, well, what are the things that I can plausibly take to be independent or at least conditionally independent of each other? And then what are the things that I have to model them as, dependent processes? Certainly things like we were talking last time about the stock market, today is not independent of yesterday and things like that. Questions about independence? Okay, so what would be the probability of obtaining a so-called turkey, which is 3 consecutive strikes? Again, not looking for a number, more of a expression, mathematical function. Nathan, number 1.
Probability of getting a strike times the probability of getting a strike times the probability of getting a strike.
Yeah, so probability of strike cubed.
Right.
So are these 3 strikes independent of each other, dependent? Andres.
Depends if you believe in the whole being in the zone theory.
Yeah, well, let's say it's the probability of a strike cubed. Does that reflect an assumption of independence or dependence? Independence. Okay, so what would be the probability of knocking down 9 pins on the first roll and 1 pin on the second roll to get a spare? What would that be in terms of a mathematical expression? Merlin?
Coming down 9 first times probability of coming down 1 condition of having knocked down 9.
Correct. Is that the same as the probability of knocking down 1 pin on the first roll and 9 pins on the second roll? Is that going to be the same number?
Yes, assuming that there's no greater difficulty in knocking down 9, and like that doesn't adjust the probability that they are.
So they're not independent either way. But is it the case that if we sort of put in 9 here for the first one and do it and then multiply by the probability of knocking down 1, given that there's 1 remaining, is that going to be equal to if we put in 1 here on the first roll and then the probability of knocking down 9, given that there's 9 remaining on the second roll? No? Correct. No. So conditioning is not, in general, a process where you can go in either order. All right. So to obtain the so-called joint probability, in general, of knocking down x1 pins on the first roll and x2 pins on the second roll, given that you started with 10, we multiply this probability on the first roll by a conditional probability on the second roll. So in symbols, it's this, ratio, two different ratios involving Fibonacci numbers, again multiplied by our indicator function that puts 0 probability on things that are impossible under the rules of Bowling. In some cases, you might be able to simplify this down to get like a neater expression, but you don't need to. You get the same probabilities whether you evaluate it in a simplified form or a unsimplified form. In this case, I don't even think you could really simplify it any more than what we have here. And we can represent this in our code by creating an 11 by 11 array or a matrix, if you will, and then doing 2 loops. So first we loop over all the elements in omega. We evaluate the probability of knocking down x1 pins on our first roll. And then we loop from 0 to 10 minus x1 and evaluate the probability of knocking down x2 pins, given that there's 10 minus x1 pins remaining. We multiply that by the probability of knocking down x1 pins on the first roll originally, and we stick that in to the appropriate element of our 11 by 11 table. And then when that loop is done, we can take the sum over all of the elements in our two-dimensional array, and it's going to sum to exactly 1 by construction because we use the general multiplication rule correctly. So these 121 things, many of which are 0, those probabilities are all numbers between 0 and 1, and they add up to 1. And we can use that matrix to look up what's the probability of knocking down, 4 pins on the first roll and 5 pins on the second roll. Okay. So someone was mentioning simulation, and that's going to be a very important aspect of semester because that's often the only way that we can go forward. But the sort of simulation analog to the general multiplication rule is something that I call composition. And so in order to implement that with just simulations in R, we need to draw a realization of x1 and use that realization of x1 when randomly drawing a realization of x2 from its conditional probability distribution. And if we do that over and over again, this is going to converge to the probability of whatever we want. In this case, the probability of knocking down 9 pins on the first roll and 1 pin on the second roll. In this case, we can evaluate that with just like analytically a little bit of multiplication. A lot of situations that we're going to talk about for the rest of the semester, we can't evaluate this analytically. We can only evaluate it with simulations, but that's not hard to do. So if I say I want 1 million simulations, I'm going to loop over those. I sample x1 like we did before. I sample x2 from the set 0 up to the remaining number of pins. Give it the corresponding probability of each of those things happening on the second roll. And if the first one is 9 and the second one is 1, I just increment my counter for the number of times that you get a 9-1 split. And then after the million iterations of the loop is over, I can compare my number of times that this happens in simulations, which is 11.9%, to the true probability that we could get by analytically evaluating this expression with 9 and 1. And it comes out to like 11.8. But as s goes to infinity, not merely stopping at 1 million, the thing on the left is going to converge to the thing on the right, which gives us a way forward when we can't calculate the true value analytically with an explicit expression. This is often going to be, good enough for even a finite but large number of simulations. Yes?
Simulation reminds me of probability consistence. Does Bayesian, is it kind of build on this notion of simulation in long-term trials?
A little bit. I would say this process of doing simulations is neither frequentist nor Bayesian. It's a property of probability. And these properties of probability we're learning about, like general multiplication rule, these are just mathematical things that you can prove. How you interpret it is really what makes the difference between a frequentist and a Bayesian, how you use it. But, you know, this sort of thing, this is just code corresponding to probability. And, you know, you could choose to use that for Bayesian things or frequentist things, and only one of those is correct. Okay, so this is the 11 by 11 table that we constructed a couple slides ago. So every element on the interior of the table is the probability of knocking down, let's say, 3 pins on your first roll and 3 pins on your second roll. So that's going to correspond to the intersection of 3 and 3, except we start calculating at 0, so whatever. Anyway, there's a 0.0072 probability of knocking down 3 pins on the first roll and 3 pins on the second roll. There is, like we said, oh, I got cut off, you know, 11.8 probability of knocking down 9 pins on the first roll and 1 pin on the second. And all these numbers sum up to 1. We saw that before. Now, a bunch of them over here are exactly 0. Why is that the case? Andres? Yeah, so the probability of knocking down 8 on your first and then 8 on your second, 0. That's where that indicator function kicks in. So yeah, you could just sort of exclude all the ones that are impossible, or you could leave them in and call them probability 0. It's a little bit easier to include them in this case. So does everybody understand what this table represents? The joint probability of something happening on the first roll and something happening on the second roll. Questions? Okay. So how can we go from Aristotelian logic to something that will tell us the probability of alternatives? And so you might ask yourself some questions like, is it true that Socrates is a man or Japan is an island? Now, or is a little bit weird because when you say or in English, it tends to mean like exclusive or, like, do you want coffee or orange juice? In the sense that like you're supposed to pick one or the other, but not both. In terms of probability in math and logic, and like obviously this case, or in general, entertains the possibility that both could be true. So Socrates actually was a man, Japan is an island. Both of those are true. And so it's true that at least one of them is true. So we can construct a truth table. So let's say we have 2 things, the first of which is true, the second of which is false. Here we use the vertical bar in R, and that means or rather than given. So true or false evaluates to true. False or true evaluates to true. And true or true evaluates to true. But if we try to do this with like arithmetic operations, the first 2 cases could be covered by addition. So if you add 1 and 0, you get 1, 0 and 1, you get 1. But it breaks down in the case where both of the things are true. If you add true and true, you get 2. And that can't make sense, at least in terms of probability. So in order to do this correctly, applying the or operation with arithmetic symbols, you have to take true, or whatever the first thing is, plus whatever the second thing is, minus the probability that they are both true. So here we have true plus false, that's 1 plus 0, minus 1 times 0, and that works out. 0 plus 1 minus 0 times 1, that works out. And the third case we handle as well. 1 plus 1 minus 1 times 1, it'll come out to 1 again. So the third row matches the first. So this can be generalized to probabilities on the 0, 1 interval. If you have two things that you don't know whether they're for sure true or false, it involves something called the general addition rule, which entails the union symbol, and this can be read as or. The upside down one, again, remember, is read as and. So this says the probability that A is true or B is true in general can be represented by the sum, the probability of A being true plus the probability of B being true minus the probability that both A and B are true simultaneously. And that is going to cover all your cases. But it's common, not always, but in a lot of situations, the probability of A and B being true both simultaneously is 0, in which case we say A and B are mutually exclusive, or sometimes we say A and B are disjoint. That means the same thing. And if this third piece is 0, then the probability that A or B is true is just the sum of their respective probabilities. So in the case of bowling, the number of pins knocked down on the same roll are mutually exclusive. You can't knock down 6 and 8 on the same roll. So the probability of getting a 6 or an 8 is just going to be the sum of the respective two probabilities. Questions about the addition rule? Note that in order to utilize the addition rule, you have to know the multiplication rule in general. Unless this is 0, then you could get away. But you need to know the multiplication rule as well to evaluate the third piece there. Questions? Okay. So going back to the same table that we had before, maybe I can make it a tiny bit smaller. Nope, that's too small. Okay. What is the probability of knocking down 9 pins on your second roll if I don't tell you what happens on your first roll? What would that be? In the back there? What's your name?
Sebastian.
Sebastian.
I guess once you sum out sort of final outcome where 9 and 8, sorry, you said 9 in the second one?
Yes.
Each of the outcome, every single outcome where 9. So you say whatever happens in the first roll is other first roll. So you kind of all their.
I like the adding. So how many things do we really need to be adding up here for the case? What's the probability of knocking down 9 pins on your second roll under the rules of bowling? Andres? Just 2? Which are those?
First 2 rows on the.
Right. So this corresponds to the probability of knocking down some number of pins on the first roll and 9 pins on the second. But most of these are 0 because you can't knock down 4 on the first roll and 9 on the second. So we only have 2 non-zero ones to worry about. The probability of 0, then 9. In addition, the probability of 1, then 9. So, but those two things are mutually exclusive because you can't knock down 0 and 1 pins on the first roll simultaneously. So these two correspond to a disjoint but exhaustive set of things that we need to add in order to get the probability of knocking down 9 pins on the second roll, irrespective of what happens on the first roll. And that is two small numbers that are like about a little less than 0.003 added together. Questions about how I came up with that? Or we came up with that? So in general, what would be the process for coming up with the probability of knocking down X2 pins on the second roll, irrespective of what happens on the first roll? What's something that would work not just for 9, but for any integer between 0 and 10 for the number of pins knocked down on the second roll? Yes?
You just sum the columns.
Sum the columns to obtain the probability of knocking down X2 pins on the second roll. And traditionally speaking, if you do the column sums here, you write them in the bottom margin of the table, which is why it's referred to as the marginal probability of knocking down X2 pins on your second roll. Also, we could sum up over the rows and write them in this margin over here. What would summing up over the rows tell us? Yes, what's your name? Mila.
It's the probability.
Probability of knocking down X1 pins on the first roll, not saying anything about what happens on the second roll. All right, so this is what's known as the first margin, second margin. All right. So the marginal distribution of the second roll, how to obtain the probability of X2 irrespective of X1. We're using the general addition rule. We're using the fact that what happens on the first roll is mutually exclusive of each other. So we're going to take the sum. This Greek letter sigma is, in this context, it's used to indicate summation. It's also a lot of times used to indicate a matrix, but when it's got the like subscripts below it, we mean, you know, sum over the indexes I, where xi is the element of the sample space for what happens on the first roll. So we want to take the joint probability of knocking down xi pins on the first roll, x2 pins on the second roll, fix x2, sum up over what happens on the first roll for this joint probability to get the marginal probability of x2 pins. And we can expand out this joint probability here as the probability of what happens on the first roll multiplied by the conditional probability of what happens on the second roll. So here I've just evaluated the numbers, but either way you can sum it up across the columns and get the margins. So here we've just worked it out in R. If we do, well, I wrote these backwards, but if we just evaluate our function, probability of omega, we get these numbers here. And if we do the row sums of the matrix on the previous slide, we get these numbers here, which exactly match up. And that is dictated to us by the rules of probability. If we take the column sums of the previous table, we get the marginal probability of knocking down x2 pins on their second roll, and we get these numbers here, which are very different from, you know, the probability of, let's say, knocking down 2 pins on your first roll. That's just 0.009. But the probability of knocking down 2 pins on your second roll comes out to 0.114. That's, you know, loosely speaking, because for this set, you tend to do pretty good on your first roll. So there may only be like 2 or 3 pins remaining. You have a high probability of knocking down 2 of the remaining ones. So the process of marginalization, summing across the rows, summing across the columns, again, that's not going to be interchangeable. Which way you do it gives you different numbers. Which way you do it gives you a different concept, or numbers corresponding to a different concept. So you have to keep that in mind when you're doing this marginalization stuff, but you already had to keep it in mind when you were doing the conditioning stuff, which, you know, goes into summing over the joint probabilities. Questions about marginalizing? Okay, let's review it a little bit. Marginal, conditional, and joint. So to compose a joint, in this case, a bivariate probability, but so we're just doing like two things right now. But in general, we could construct a joint probability of any number of things. But let's just focus on the case with two, like two rolls in bowling. So to compose a joint probability, you multiply a marginal probability by a conditional probability. You multiply the marginal probability of knocking down X1 pins on the first roll by the conditional probability of knocking down X2 pins on the second roll, given that 10 minus X1 pins are remaining. Multiply those two probability functions together to get the joint, in this case, bivariate probability of knocking down X1 pins on the first roll and X2 pins on the second roll. That's how we compose a joint probability. To decompose a joint, in this case, bivariate probability, you add the relevant joint probabilities either down the columns or over the rows to obtain a marginal probability. So in the first case, we start with a marginal and conditional, we get a joint. If we have a joint, we can sum over the rows, we can sum over the columns, depending on which one we're interested in, to get a marginal probability of knocking down X1 pins on the first roll, irrespective of what happens on the second roll, or knocking down X2 pins on the second roll, irrespective of what happens on the first roll. So we can either compose a joint probability with a marginal and a conditional, or we can decompose a joint into either marginal by using addition. And to obtain a conditional probability, we divide the relevant joint probability by the relevant marginal probability. And that can be seen by going back to the general rule for multiplication. The probability of A and B both being true can be written as the marginal probability of B being true times the conditional probability that A is true, given that B is true. But this on the left is also equal to the marginal probability that A is true multiplied by the conditional probability that B is true, given that A is true. And if these two things are equal to the same thing, namely the probability that both A and B are true simultaneously, we can just set these equal to each other, rearrange this a little bit by putting the probability of B over in the denominator over here, and we're left with this expression. The conditional probability that A is true, given that B is true, is equal to the marginal probability that A is true, multiplied by the conditional probability that B is true, given that A is true, all divided by the marginal probability that B is true, assuming that it's the case, the probability that B is true is positive. Since we're conditioning on B, we're saying what's the probability of A is true given that B is true. If B is impossible, then this doesn't make sense. We can't be dividing by 0 here. But if B is any kind of a positive number, and it's going to be less than 1, then this is a valid expression for the probability that A is true, given that probability, or given that B is true. So in order to obtain the conditional probability of A given B, we have to take the joint probability of A and B together, here expressed as their composition, and divide by the marginal probability of B in order to get the thing that we're looking for on the left. Questions? So So we can go from a marginal and a conditional to a joint. We can go from a joint to either marginal. And we can go from a joint to either conditional by taking the joint and dividing by the marginal of the thing that we want to condition on. And this will yield a valid probability function. And that's what's known as Bayes' rule. It's really just a rearranging of the general multiplication rule. But this is really the process that we want to go through for the rest of the semester to get the thing on the left, the probability of A being true, given that B is true. We want to evaluate the three things on the right and, you know, multiply them together, divide, etc., to get our conditional probability. Questions? All right. Example of Bayes' rule. What's the probability of knocking down 3 pins on the first roll, given that 4 pins were knocked down on the second roll? So imagine you walk into a bowling alley, you hear someone say, I knocked down 4 pins on my second roll, but you don't see what happened on the first roll. It's like missing data or whatever. What's the conditional probability of knocking down x1 equal 3 pins on the first roll, given that the person who you assume to be honest told you that they knocked down 4 pins on the second roll? How would we evaluate that? Using Bayes' rule, because this is a Bayesian class. And because we just got through devising Bayes' rule, which is not all that hard to do. And number one.
It would just be probability that you knock down 4 on the second roll times probability that you knock down, I guess, A given 4, which is 3. 3 given 4. Given that you knock down 4, given that you knock down 3 pins on the first roll, divided by the probability that you knock down 4 pins. But the first one should have been the probability that you knock down 3 pins on the first roll. That I missed it.
Anybody want to summarize that? I think what you were trying to say was that. Take the joint probability of knocking down 3 on the first roll and 4 on the second, divide by the marginal probability of knocking down 4 on the second. That is the 3 things on the right-hand side of Bayes' rule. Gives us the thing on the left, which is what we were seeking, the probability of knocking down 3 on the first, given that 4 on the second. So if you go back to this, okay, here's all the 121 things, most of which are 0, that could happen. But the person told you, I'm in column 4, right? Or column with header 4. So this whole thing adds up to 1. But when you get new information that x2 was 4, you know you're in this. And all this other stuff over here and all that, that didn't happen. So we got to get all this probability and all that probability like into column 4. So we take what happens in column 4, divide them by the sum of what's in column 4, which is equal to 1 minus the sum of everything in all the other columns. And so we renormalize the probabilities to get something like 0.03222 here. And so Bayesians generalize this. They take A to be, you know, your beliefs about whatever you don't know, and B to be whatever information you have that you do know. This was in the news the other day. Apparently everyone in Hawaii got a text message saying North Korea had launched a missile and they're all going to die. So if you get that text message and you're a Bayesian, you might want to quickly figure out the probability that you are going to get hit with a missile, given that you got a text message saying that you are going to get hit with a missile. So that can be represented. So probability of missile given text as the marginal probability that North Korea will launch a missile. Seems small, but you know that guy is bros with Dennis Rodman, so you never know. Times the probability that you get sent a text given that there's a missile launch. So that seems pretty high. I didn't actually know that they would send text messages in that situation, but apparently they do. Divided by the marginal probability of getting a text saying that there's a missile coming, which can be expanded using the general addition rule as the thing in the numerator, probability of missile times probability of text given missile, plus implicitly in the denominator here, we have the probability that there's no missile, so that 1 minus the probability of A, multiplied by the probability of a text given that there's no missile coming. So maybe like hackers got into the system, maybe they were doing like a test of the text message thing. Apparently somebody hit the wrong button, etc. And so actually it turns out the probability that you're going to die given that you get a text message saying that you're going to die is not that big. But you could do that if you use Bayes' rule. Now, I think, you know, most of the tourists who were in Hawaii at the time were not using Bayes' rule. And so it was a more alarming situation than what it probably should have been. They were really just evaluating, you know, the probability that you get a text given that a missile is coming, but really the missile wasn't coming. So just looking at this gives you a very incomplete picture of the thing that you wanted to know. Probability of missile given text. All right, so that's in a simplified form, the process that we want to be using over and over again over the course of the semester. How can we get the probability of A given B, where A is what we don't know and B is what we do know? And that's just really a fundamental thing, obviously, for Bayesian inference. But that idea really of just induction given data is just a fundamental idea of data analysis, science, social science, you know, what have you. So we're going to be doing that a lot. Okay, that's it for today. I have some forms. Those of you who are not registered, apparently SSOL is just completely broken. So you have to fill out a paper form. Those of you who have not done so yet, you probably should email me. I'll add you in the meantime as an auditor on Courseworks. You can fill this out. You don't have to get anybody's signature. You just have to take this back to the QMSS office, which is on the 8th floor of IAB. So you can grab a form. All right. One more. Yes.